Welcome to Lecture 13. We're still working through higher order ODEs, which is Unit 2 of our course. And so in the previous lecture, well, we did multiple things, but one thing, I guess the thing we did right at the end was the method of the reduction of order. Okay, so what this method was is if we had a second order linear ODE and we have one solution for the second order homogeneous ODE, then we could actually find a second solution using the first solution and using this method of reduction of order. Okay, so this is going to come back to help us today. Okay, but the main topic that we're working on today is homogeneous linear equations with constant coefficients. So again, we're specializing even more right now. So we're looking at homogeneous ODEs, so right hand sides which are 0. Linear equations, okay, so linear ODEs, and in fact we're going to focus on second order in this class, but now we're even going to specialize even more, and we're going to look at the case that our coefficients in front of the derivatives are not functions of x, but are constants. Okay, and so we're going to learn about something called the auxiliary equation and the discriminant, and we're also going to learn about 3 possible cases, which will give 3 possible solutions, and I think we'll get through about 2 of these in this class, and we'll save the third one for tomorrow's class, for lecture 14. Okay, so jumping in, so let's consider the second order linear ODE with constant coefficients, and it should also say second order homogeneous linear ODE with constant coefficients. Okay, so A, B, and C here are all real numbers. A cannot be equal to 0. Otherwise, in fact, we would not have a second order ODE, we just have a first order ODE. So A cannot be 0, and of course notice that the right hand side is 0, and therefore we have a homogeneous equation. So these constants A, B, and C are obviously continuous for all values of x. Then by the existence and uniqueness theorem, this ODE has solutions for all the real lines, so all values of x. Okay, so the general solution is given, the general solution of this homogeneous second order linear ODE is given by the superposition of the 2 fundamental solutions, y1 and y2. Okay, where c1 and c2 are just some constants. And so our job in this lecture is to start to learn how we can find these solutions, these fundamental solutions, y1 and y2. Okay, so again, c1, c2 are constants, y1, y2 are linearly independent solutions to the ODE. So therefore they form a fundamental set of solutions to the ODE. So again, in this class, how do we find y1 and y2? Okay, so, well, what we might like to do is try a test solution. Okay, so we're going to take some number m in the real numbers, so r, m and r, m is just a real number, and we're going to try the solution y is equal to e to the mx. Okay, so why do you think that this may be useful for us? Well, we want some function where we take its derivative and again its second derivative, and then we multiply that second derivative by a, the first by b, and the function itself by c. When we add those together, we want it to add up to 0. Okay, so we don't want a function like, for example, sine, which will turn into a cosine when we take its derivative, or we don't want something like a logarithm, which will turn into a 1 over x. Log of x goes to 1 over x when we take its derivative. We want functions that will be the same type when we take its derivative, and in fact even its second derivative. So exponential satisfies that property, and that every time we take a derivative of the exponential, we still get this term e to the mx back, where m is just some constant and x is the independent variable. So let's take the two derivatives of this function y. So we have y prime is equal to m e to the mx. So we just write the function e to the mx and multiply it by the derivative of the exponent. And then similarly, if we take its second derivative, we're simply going to get m squared e to the mx. And so now let's use these three relations in this second order linear homogeneous ODE with constant coefficients. Okay, yeah, so we'll substitute these functions into the ODE. Okay, if we do that, well, here we get a times y double prime plus b times y prime plus c times y equals 0. Okay, well, the exponential of mx is never equal to 0 for any finite value of x, so we can easily take out this constant factor and divide through by it. So therefore, if we divide both sides by e to the mx, then this equation simplifies to am squared plus bm plus c equals 0. Okay, and of course this is just a quadratic equation for this unknown number m. Okay, in fact the values of a, b and c we already know because, well, somebody has given us a differential equation, so we would be able to interpret what the values of a, b and c are. But we can solve for the values of m using the quadratic formula. Okay, this equation am squared plus bm plus c equals 0 is called the auxiliary equation. Okay, so I'm going to refer to the auxiliary equation quite often throughout this, throughout Unit 2 and beyond. Okay, so of course we've got a quadratic, which means that we're going to have two solutions to this equation, or two roots to this quadratic, or at least should I say possibly two roots to this quadratic. We could have a repeated root, of course. So what are the two solutions? The two solutions of this auxiliary equation, I'm going to label m1 and m2. So of course they're negative b plus the square root of b squared minus 4ac, all divided by 2a. And the second solution is negative b minus the square root of b squared minus 4ac over 2a. Okay, so there are two solutions there, m1 and m2. Of course they could be, m1 could equal m2 if b squared minus 4ac equals 0. Okay, so I'm just cleaning up my my slide here. So now we have the ODE, we have the auxiliary equation, and the two roots, the two solutions to the auxiliary equation. So this is the key information. So now this thing underneath the square root, b squared minus 4ac, we call that the discriminant, and we often represent that by this delta. So this is the Greek letter delta. It's a capital delta. So we call it the discriminant. And so the value of the discriminant is going to determine the type of solution we have. Okay, and what do I mean by that? So we can have three possible cases, right? Case 1, if the discriminant is greater than 0, case 1, if the discriminant is greater than 0, m1 and m2 are real and distinct. The two roots of this auxiliary equation give us two real numbers not equal to one another. Okay? Because when the discriminant is positive, the square root of the discriminant gives us a real number. Okay, so case 1, discriminant positive, the two roots m1 and m2, or the two solutions to the auxiliary equation, are real and distinct, two unique numbers. Case 2, I mentioned, when the discriminant is exactly equal to 0, that is when b squared minus 4ac equals 0, then m1 and m2 are is a real number, and in fact they are equal to one another. So we have a repeated root. Okay, and then finally case 3, when the discriminant is negative, well, we end up taking the square root of this discriminant. So we take the square root of a negative number, which of course gives us complex conjugate roots. So we're appealing back to our first year calculus here. but I don't think that's too hard to recall. So what I want to do now is, for the rest of this class, this lecture, we're going to go through case 1 and case 2 and look at what our solutions are in each case, and then case 3 we'll carry on that in the next lecture. So beginning with case 1, the case where the discriminant is positive and our two roots are real and distinct. Okay, so I've got the ODE up the top here, our second order linear homogeneous constant coefficient ODE. We've got the auxiliary equation in the next line and the two roots. Okay, so case 1, discriminant is positive, M1 and M2 are real and distinct. The two solutions then are going to be y1 equals e to the m1x. So recall that our test function was y equals e to the mx. Well, here we found that m1 is one number and m2 is a separate number. So our two solutions are e to the m1 times x, and their second solution is e to the m2 times x. Okay, so these are our two solutions that satisfy this ODE, constant coefficient linear homogeneous second order ODE. The question, of course, then becomes, do these two solutions form a fundamental set of solutions so that we can write down the general solution to this ODE? Okay, so in other words, are they linearly independent? Let's calculate the Wronskian. Okay, so the Wronskian, we can write down the two functions, e to the m1x, e to the m2x. So this is y1 and y2. And in the second line, to create a square matrix, we need to calculate the derivative of each of these, which is again rather easy, because the derivative of e to the m1x is just going to be m1 times e to the m1x. And similar for the second equation. Okay, we've got a 2 by 2 matrix. We need to take the determinant of this 2 by 2 matrix, which again is quite straightforward. We get e to the m1x times m2 times e to the m2x. Take away m1 times e to the m1x multiplied by e to the m2x. So if I write that out, I can, well, when I'm multiplying exponentials, I end up adding them. So I end up with, in the exponential, e to the m1 plus m2 times x. And out the front, I get m2 minus m1. Okay, and this is never equal to 0, and I can explain why. So this exponential is never equal to 0. The exponential, in fact, is never equal to 0, except for at some negative infinity, or some point where the argument of the exponential goes to negative infinity. So for any finite value of x, this exponential is always positive. m2 minus m1 is also never equal to 0, because in case 1, where the discriminant is positive, m1 and m2 are real numbers, but significantly they're distinct. They are not the same number. Okay, so they are not the same number, therefore this m2 minus m1 is never 0. Therefore I can conclude that y1 and y2 here in the red box are linearly independent solutions to the ODE. Okay, they form a fundamental set of solutions, and we can form from that fundamental set the general solution of this ODE, of this second order linear homogeneous constant coefficient ODE. And we do that by simply taking the superposition or the linear combination of these two solutions, y1 and y2. So c1 and c2, of course, are constants here. And this is the general solution. c1 times e to the m1x plus c2 times e to the m2x. This is something that I really would like you to burn into your memory. In fact, the three cases we're going to be looking at here are going to come up again and again and again in this class. So please burn this lecture and the next lecture into your memory, because we will use it almost every lecture. Okay. Let's look at an example though with some real numbers. Okay, so let's look at this this second order linear homogeneous constant coefficient ODE, where our coefficients are 2, -5, and -3. Okay, well, we've identified a equals 2, b equals -5, and c equals -3. Related to, okay, I've just made it a little bit obvious here. A is always the coefficient in front of the second derivative, b is always the coefficient in front of the first derivative, c is always the coefficient which is multiplying y. Okay, so, well, our auxiliary equation would be a times m squared, plus b times m plus c equals 0. So I'm needing to solve this equation, which of course I can do using these two roots here, m1 and m2. Okay, well let's write that out. Our solutions m1 and m2 are 5 plus or minus the square root of 25 minus 4 times 2 times -3. Well, I can already see that this discriminant, this thing under the square root, is going to be positive because, well, I've got 4 times 2 times -3. And I'm taking that away, so it's going to be 25 plus a number, right? Okay, so it's just going to be 25 plus 24. Okay, so we end up with 5 plus or minus the square root of 49, which of course is 7, divided by 4. So if we calculate that, 5 plus 7 divided by 4 gives us 3. 5 take away 7 divided by 4 gives us -1/2. So our two roots, our two roots to the auxiliary equation, or our two solutions to the auxiliary equation, you could say the two roots to this quadratic equation. But anyway, the two solutions to this auxiliary equation here are 3 and -1/2, which means we can form the general solution to this ODE as y of x equals c1 e to the 3x, so 3 there being m1, plus c2 times e to the -1/2 x, where -1/2 being m2. This is the general solution to the ODE. Of course, we don't know the value of c1 and c2. We could find that if we had an initial value problem, but right now we were just solving the ODE itself. So actually, this is the first second order equation that we've actually solved, right? So this is quite cool that we're able to do this now. And in fact, like I say, if you burn this into your memory, you are able to do this really quickly. So I really hope that you will practice these and get these down to an art form, because being able to do this rapidly and accurately is going to save you a lot of time and tests. Okay, so case 1 is fairly straightforward and I think fairly simple. Well, the cases do get somewhat more complicated, but not too much more. So let's have a look at case 2 now. So case 2 is where that discriminant b squared minus 4ac is equal to 0. Okay, and if that means if it's equal to 0, m1 equals m2. So we can just write m1 equals m2 equals just some number m in that case, because it's the same number. And in fact, we know the value of m because m is always going to be -b over 2a, because the rest of this stuff is 0. So m is -b over 2a. We only have one solution in this case. We only have one root to this quadratic, only one solution to this auxiliary equation. So in fact, we only have one solution here. y1 of x, the solution y1 is equal to e to the mx. To be able to form the general solution to the ODE, we need two solutions, because we need a fundamental set of solutions. So we're missing one solution. But wait a minute, didn't we deal with this problem last lecture? If someone gives me an ODE, a second order homogeneous ODE, with only one solution, I can generate a second solution. Okay? If we have one solution, we can find a second solution using the method of reduction of order. Okay, so remember, the method of reduction of order worked for an ODE in this form here. Y double prime plus p of x, so this is any function of x times y prime, plus q of x, this is any function of x times y, equals 0. So in our case, of course, we're dealing with something that is a function of x in terms of it's a constant. Okay, and because a is not equal to 0, we can always divide through by a to get this y double prime on its own. Okay, and recall, using the method of reduction of order, the second solution can be generated from the first using this integral here. Okay. So now our ODE is given by a y double prime plus b y prime plus c y equals 0. We can identify these functions p and q, although we only need p. So p is going to be, I have to divide through by a here, p is going to be b divided by a. Okay, a is not non-zero. Okay, let me tidy up the screen here so I have some more space. Alright, so I have my first solution, which I haven't written on here for some reason. My first solution is e to the mx. I can generate my second solution using this equation. So substituting in for y1, e to the mx, because our first solution was e to the mx. Substituting for p, the constant b over a. So this is a constant, which makes this integral easy. Y1 squared, while e to the mx squared is e to the 2mx. This is how you square exponentials. Let's calculate this integral, of course. So this is quite easy. Well, okay, sorry, we've already done the integral here. We get exponential of negative b over a times x. We can combine these integrals, these exponentials here, because when we divide exponentials, we simply subtract the arguments. Okay, so the exponential of negative b over a times x divided by e to the 2mx is going to be the exponential of negative b over ax minus 2mx. And so I've just written that here, negative b over a minus 2m times x. Okay, and again, this integral is relatively straightforward, but we can even simplify it even further when we remember what is m. Okay, well, m, in the case that the discriminant is equal to 0, in other words, the square root, we take the square root of 0, which is 0, m is actually negative b over 2a. So m is negative b over 2a. So if I substitute 2 times m, we get simply negative b over a. In the exponential then I get negative b over a minus b over a, okay, which is actually just 0. So I get e to the mx times the integral of the exponential of 0 dx. The exponential of 0 is just 1. Okay, so I'm integrating 1 with respect to dx, and therefore the integral of 1 is just x. So our second solution to our ODE is therefore simply x times e to the mx. Okay, so thankfully we had that method of reduction of order so that we can find our second solution. So case 2, if the discriminant is equal to 0, two solutions to this ODE are e to the mx, y1 is e to the mx, and the second solution, y2, is x times e to the mx. Okay, but we better check that these solutions are linearly independent if we want them to form a fundamental set of solutions. So here we have the start of the matrix e to the mx, x e to the mx. We need to take the derivative of each of these terms. So of course e to the mx is, if I differentiate that, I get m e to the mx. The second term is slightly harder because we have a product rule. So if I keep the exponential constant, I get differentiate x, we get 1 times this exponential plus x times m times this exponential. So if I substitute that in here, it looks like this. And then I have to take the determinant of this square matrix. So e to the mx multiplied by this bottom right term minus the other two terms multiplied together. Okay, so this is what I get when I take the determinant. And you can already see that the exponential, the mx times the exponential is going to cancel here, right? So we're going to end up with 1 times e to the 2mx. And again, this is never 0 for any finite value of x. Therefore, these two solutions, y1 equals e to the mx and y2 equals x e to the mx, these two solutions form a fundamental set of solutions, and therefore the general solution to the second order linear homogeneous constant coefficient ODE in the case where the discriminant b squared minus 4ac equals 0 is given by C1 times e to the mx plus C2 times x times e to the mx. This is the general solution to case 2 where the discriminant is equal to 0. Okay. Always remember that these three cases that we're dealing with, case 1 that we've dealt with, case 2 that we've just derived, and case 3 that we'll deal with in the next lecture, this is only true for second order linear homogeneous ODEs with constant coefficients. A, B, and C are constants here. This is not true in general. These solutions are different if the coefficients in front of the y, y prime, and y double prime, if they're functions of x. Okay, this is only in the constant coefficient case. Okay, but let's look at an example here now. So we have y, the ODE y double prime minus 10y prime plus 25y equals 0. So let's identify our auxiliary equation here. am squared plus bm plus c equals 0. A is the coefficient in front of y double prime, so it's 1. B is the coefficient in front of y prime, so negative 10, and c is 25, the coefficient in front of y. Let's calculate b squared minus 4ac. Well, b squared, negative 10 times negative 10 is 100. 4 times a is 4, times c is 4 times 25, which is 100. So we end up with 100, b squared is 100, minus 100. So in this case, our discriminant is equal to 0. Okay? Our discriminant is equal to 0. B squared minus 4ac equals 0. Therefore, we only have one root, or one repeated root, or one repeated solution to this auxiliary equation, which is going to be minus b over 2a. Okay, well, minus b is 10 over 2a is 2, so 10 over 2 is 5. So I'm not sure why I put the plus or minus 0 here, but the only solution we have is 5. Okay, we have a repeated root. Therefore, because I know the form of the general solution, I know that the solution, the general solution to this ODE in case 2, where the discriminant is equal to 0, as we have calculated, is simply C1 times e to the 5x plus C2 times x times e to the 5x, where the 5 is the repeated root here, the root of the auxiliary equation. So again, I hope that you'll go back and really memorize the general form of the solution, or even understand where it came from so you can derive it if you need it. But the point is, when you're sitting in a test environment, I want you to be able to for these constant coefficient second order linear homogeneous ODEs, I want you to be able to calculate the roots extremely fast, which, well, as fast as you can enter them into the quadratic formula. And then once you know which case you're working in, case 1, case 2, or case 3, be able to simply write down the general solution from memory. Okay, if you can do that, you will save yourself a lot of time, and it will help you for sure in this class. So in the next lecture, we will talk about case 3, the case where the discriminant is negative. Okay, thank you very much.